Dear learners, greetings from IIT Guwahati. We are in the week 2 MOOCs course, that is computational gas dynamics. So, in this week we started with normal shock and oblique shock waves. So, in this lecture 2 of normal shock, which is part 2, I will touch upon some of the other property variations across a normal shock, that is entropy change across a normal shock. Then we will introduce two fundamental theorems. One is Crocos theorem, other is Huguenot equations, that will give you the relations between thermodynamic parameter and fluid mechanics parameter about the information in the flow field which takes place across a normal shock. So, these two Crocos theorem and Huguenot equations are two fundamental basics to calculate some of the important inferences for a normal shocks. Then these two information gives rise to shock wave as a compression mechanism. Normally, we come across the compression process in a thermodynamic diagram, but in a gas dynamics course, we will introduce another irreversible mechanism across which there is a change in the entropy, and through these irreversible mechanisms, we can think of a compression process, and in fact, it is highly beneficial for many kind of applications, particularly high speed flights involving ramjet and scramjet engine. So, to give the brief introductions what we have covered in our last lecture, that is normal shock relations, we define this normal shock is a very thin region across which properties change drastically in one directions, and the shock wave is perpendicular to the streamline. So, if you think this as a normal shock, so what we see that the streamlines which is entering, which is at supersonic flow with its given conditions of thermodynamic properties and fluid mechanics properties, and when it crosses the shock wave, the pressure shoots up, temperature shoots up. These are static pressure and temperatures, but stagnation pressure drops, static temperature remains constant, static density increases and velocity drops, and Mach number becomes subsonic. So, this information we get through these equations which is given here, and that is called as Frankel relations, which gives the relation between M2 and M1. So, what it says, if your M1 is greater than 1, M2 has to be less than 1, which means Mach number behind a normal shock is always subsonic. So, these informations are related in terms of static density ratio, velocity ratio, pressure ratio, enthalpy ratio, temperature ratio. We also have relations, that is stagnation pressure ratio, stagnation density ratio, stagnation temperature ratio, and obviously the stagnation temperatures remains same across a normal shock. And again another important information that talks about a normal shock is Rayleigh-Pitot equations. This is one of the important equation which is used for experimental experiments in a supersonic flow when we take measurements using a Pitot tube. So, this is what about the summary. Now, moving further from this point, what we are going to discuss in this lecture is, first part is entropy change across a normal shocks. So, we mentioned that entropy is a thermodynamic phenomena, and it is derived from the second law of thermodynamics. So, based on the second law of thermodynamics, the entropy parameter decides the directionality of a process or spontaneity of a process. A process should proceed in certain directions in which entropy must decrease, and one of the fundamental principle what we call as entropy principle, that tells that entropy of universe always increases. That is called as increase in the entropy principles. So, with this background, we will try to see what happens to the flow field when a streamline crosses a normal shock. So, by definition, a normal shock is a discontinuity in the flow mediums. And if you see that your upstream conditions are before the shock, the flow field is almost isentropic in nature, and downstream of this normal shock is also flow fields are isentropic in nature. But what happens, this flow properties across a normal shock, so it introduces a discontinuity in the flow field. So, this discontinuity arises in a very thin regions. So, what we say is that but however, the streamline crosses the normal shock. So, it is something like physically it means that when a streamline approaches a normal shock, it has certain property. Just after it crosses the shock, there is a sudden change in the properties. So, this is nothing but the discontinuity in the flow field, and we are going to get the we have already explained that how the downstream properties and upstream properties are related in terms of their ratio for a given upstream Mach number. But now, why one information was clear, that Mach number across after the shock is always subsonic, and such informations we can say that why such information that can be provided to the information of entropy as well. So, we will try to see, since we have pressure and temperature change across a normal shock. So, by second law we must say that this also has to deal with something with entropy change, because if you look at the entropy equations, that is entropy change across a normal shock can be related to the static temperature ratio and static pressure ratio. So, this is nothing but your entropy equation that we get from thermodynamic analysis. And since we have we know this pressure ratio across a normal shock, that is static pressure ratio across a normal shock, and static temperature ratio across a normal shock, then one can easily obtain the entropy change across this normal shock. So, this is one information that is done with respect to static pressure ratio and static temperature ratio. But again, such information can also be correlated with stagnation conditions. So, although we say information this, but what happens to stagnation pressure? And we have already saying that stagnation pressure drops. Why it drops? That answer we are going to get by calculating the entropy change. Now, for the time being, we can say that when you look at the actual flow phenomena S2 and S1. So, this is a actual flow phenomena that occurs across a normal shock. But I have already mentioned that flow field before the normal shock, flow field after the normal shock can be considered isentropic throughout. So, this is the basic assumption. So, based on this we introduce this stagnation pressures and stagnation temperatures. So, what we imagine that if you take the upstream conditions, that is for example, if state 1, that is state 1 brings isentropically to a state 1A, and state 2 is hypothetically changes its state to 2A. So, basically S2, S1A and 2A, these are isentropic event. And so, isentropic event means state 1 is brought isentropically to rest, 0 velocity, or stagnate the flow from initial condition 1 to a state 1 isentropically, and you stagnate the flow isentropically from the condition 2 and it comes to 2A. So, this process that undergoes isentropic manner and the flow is stagnant at 1A and 2A. So, once the flow is stagnant at 1A and 2A, so we can say that at 1A we say its stagnation pressure is P naught 1, at 2A its also stagnation pressure is P naught 2. So, if you do these things, but since both the states are brought isentropically, so you can rewrite the equation in terms of stagnation pressure value. That means, you can write S2 as S21 2A and S1 as S1A, take the difference. So, when you are taking this entropy difference at this state, then we must replace this with corresponding temperature and pressure. Now, corresponding pressure of temperature, corresponding temperature for 2A will be T2A and that will be T1A. Here it will be P2A by P1A. But we know that S2A is equal to S2 because this process is isentropic, S1A is equal to S1, and from our previous discussions, stagnation pressure do not change, stagnation temperature do not change across a normal shock. So, this relation holds good. So, which means this term vanishes. So, when this term vanishes, we rewrite again that S2A as S2 and S1A as S1 because these are two hypothetical states for the corresponding actual state. So, we can rewrite this equation as S21 minus S1 is equal to minus R ln P naught 2 by P1. So, this is an logarithmic relations. So, from this the stagnation pressure ratio can be interpreted as P naught 2 by P naught 1 and that is equal to e to the power minus S2 minus S1 by R. So, this is the very basic fundamental relations, and since there is it's a exponential relations, and this relation gives rise to the fact that since this term is less than 1, which means stagnation pressure must drop. So, this is how we get the information that stagnation pressure drops across a normal shock, entropy increases, and based to this and also from the Prandtl relations we say Mach number after the normal shock is always subsonic. Then moving further, if you go deep into the further entropy equation and entropy analysis, try to correlate the entropy relations with respect to upstream Mach number. If you look at this equation, that is, let us find out some of the cases that when M1 is equal to 1, S21 minus S1 is equal to 0, which means S2 is equal to S1, which means that the normal shock does not exist here. Entire flow field is isentropic. Now, when you say M1 is greater than 1, your S2 minus S1 is always greater than 0, that means S2 is greater than S1, which means the entropy, this side we have S2 and you have S1, which means entropy after the shock always higher than S1. This is the second case, and that means entropy always increases. So, this is true, but we have it. Now, let us see if M1 is less than 1. When M1 is less than 1, S2 is less than S1, which means such a condition is not possible. So, M1 is less than 1 means flow is subsonic. And in a subsonic flow, we cannot use that equation. That means, the entropy increase in the entropy is not allowed in a subsonic flow, because there is no existence of a shock waves. So, which in other words says that Mach number behind the normal shock is subsonic, ahead of the normal shock is supersonic. Stagnation temperature and total enthalpy remains constant across a normal shock. Stagnation pressure and stagnation density decreases across a normal shock. So, this information we get from the entropy equations, and for subsonic flow entropy decreases across a normal shock, which is almost an impossible situation, and because it will violate the second law of thermodynamics, which means shock waves do not exist in subsonic flow. So, this is the fundamental theory. Again Mach number should decrease, and to satisfy this equation we have already shown that Frankel relation also says that Mach number should decrease. All static flow properties have large and steep gradients. So, as if it is a step functions within a very short thickness. Then moving further, we are now going to introduce another parameter or another theorem, that is called as Crocos theorem. Normally when there is a steady flow field with gradient in the enthalpy or entropy, and that flow field is treated as highly irrotational. When there is a gradient and when there is an entropy gradient exists along the flow field, that has to be highly rotational. So, across a normal shock we have seen there is a steep gradient in the entropy, and the stagnation pressure drops exponentially, which means there is a definite correlation that these mathematical concepts can be utilized to certify that what is the nature of the flow, whether it is a rotational and irrotational, which is called as flow behind normal shock is highly rotational. So, this conclusion we are going to arrive through a mechanism or through mathematically by a theorem called as Crocos theorem. So, for a compressible flow, a relationship can be established between kinematic parameter of the fluid flow with the thermodynamic entropy change for the fluid, and this so for that the Crocos theorem relates the fluid parameter, that is fluid vorticity, with entropy change, that is thermodynamic parameters. Now, let us see how these two things are related. So, let me revisit the Crocos theorem and what is the derivations. For that, little bit of knowledge of vector notations is required, like curl, divergence, gradient, all the information. I hope since basic mathematics courses would have taught this concept, but however our main emphasis would be that end results for the Crocos theorems. So, let me start that equations, that is Euler equation. When it is written for unsteady flow, we can write that rho dou v vector by dou t plus rho v vector into gradient into v vector, that is equal to delta p. So, these equations can be simplified as gradient of p by rho in terms of velocity vector, and again this is the fluid mechanics equations, and corresponding thermodynamic relations we write TdS is equal to dH minus VdP. So, specific volume can be related to as 1 by rho, and we can also introduce the term what is called a total enthalpy, that is H plus V square by 2. So, replacing H as H naught and rewrite this TdS equations, this can be represented in this form. So, we have two fundamental equations, one we get from Euler equation, second we get from thermodynamic TdS relations, that is second law, combined first law and second law. Then mathematical tool is introduced. So, this is a fluid concept, this is the thermo concept, and third this is mathematics, that is vector identity. So, what we do is we recall that if you see this particular TdS relations, it involves terms, that is v vector dot of gradient into V vector and gradient of V square by 2. So, these two information is represented here, and this is nothing but a vector identity, and this is equal to this. That means, cross product of V vector into gradient into cross product of V vector. So, this is what is vector identity. So, we try to introduce T into gradient of S, that here S stands as entropy in terms of total enthalpy dV vector by P, and here we introduce this vector identity term here. So, now the Crocos theorem that can be derived. So, this particular relation that we obtained, that left hand side of this equation, that is left hand sorry, in this case we have say right hand side of this equation, that is T into gradient S, that is thermodynamic parameter. Here H is the enthalpy. Okay. So, these two are thermodynamic parameters, and these two terms dou V vector by dou T and this cross product term, this is a fluid mechanics parameters. And if in a and this is what this relation holds good for all types of flow field, and this is true for unsteady flow, and for steady flow this term vanishes. So, we rewrite this equation as follows, that is one side we have cross product term, other side we have thermodynamic term. Basically, one side we have fluid mechanics term, other side we have thermodynamic parameter. Now, we have already told that across a normal shock, that is T naught 1 is equal to T naught 2, that means H naught is equal to constant. So, which means that this term vanishes, that is delta S 0 is equal to 0, and we say delta S greater than 0, that means this delta S cannot be 0 across a normal shock, this is always greater than 0, and which means gradient of velocity vector, that is we can derive from this here, that gradient of velocity vector or cross product of gradient of velocity vector and cross product of gradient and velocity vector cannot be 0, and this particular term is nothing but your angular velocity. That means, fluid element will have angular velocity, because the this cross product is not equal to 0, and this angular velocity is nothing but angular velocity omega vector is correlated with respect to term called as vorticity. So, the summary that we get, that omega vector cannot be 0, that means angular velocity cannot be 0. So, this gives the theory that behind that flow field behind a normal shock is highly irrotational. We cannot, so highly rotational. So, flow field behind a normal shock is highly rotational, it cannot be irrotational flow. So, it means we will say vortices that drops in when the fluid element crosses the normal shock, that means streamline in experiences vortices when it crosses normal shock. Another important relation that we get from this case, which is called as Higgins equations. So, Higgins equation talks about the thermodynamic behavior when the streamline crosses the normal shock. So, it can be said that the changes across a normal shock can be independently assessed purely on thermodynamic aspects without involvement of any reference velocity or Mach number. So, here we will not talk about Mach number, although Mach number is essential for such a case of thermodynamics. For the time being, we will not introduce that, but we are going to assess this normal shock equations as a thermodynamic evidence. and based on this we are going to say that how that equation is related to fluid mechanics phenomena. So, we say that pressure increases across a normal shock. So, thermodynamic viewpoint is that there is a compression process. Now, that compression process, how that can be independently assessed through this thermodynamic equation. This is our viewpoint. So, we have to revisit three equations, that is continuity equation and momentum equation and energy equation. From continuity equation we can independently find the velocities u2 and u1. From the momentum equations we can independently find u1 square and u2 square, and from energy equations we have u1 square and u2 square, and put this u1 square and u2 square here in this energy equations. Then simplify. Ultimately, when you simplify this equation, we arrive, and this enthalpy term here is represented as by internal energy E plus P by rho. Now, when you simplify this equation, we find the internal energy change, that is E2 by E1 is equal to P1 plus P2 by 2 into this whole 1 by rho 1 minus 1 by rho 2, or P1 plus P2 by 2 into specific volume change. Here there is a negative sign. So, this equation can be said that internal energy change across a normal shock is related to average pressure into change in the specific volume. So, this is nothing but the derivation evidence that we get the first law of thermodynamics for an adiabatic process. Now, same thing we are trying to represent graphically. So, using this information, that means from our previous discussions we arrived at this particular relations u1 square in terms of P2 into u1 square is equal to P2 minus P1 divided by rho 2 minus rho 1 into rho 2 by rho 1, and from this we get an equation that is called pressure change between two states to the specific volume change is a function of u1 square by u1 by v1 whole square, which means let us say that we in a PV diagram, this is the thermodynamic PV diagram, we normally compression process is represented in thermodynamic diagram, that is PV diagram. We say it is P and V, and we define that state as V1, that is initial state, that is state 1, and once you define this initial state at particular U1. So, at a particular upstream position, that is for particular U1, we these coordinates are specified as P1 V1 here. Now, from this point if you draw a slope, negative slope, because this negative slope of minus u1 by v1 square, draw a negative slope and keep moving it. So, state 2 will be defined. Another point we can draw for another number, we can draw for different value of u. So, for u1, u2, u3 likewise from this point we can draw along this with this slope, we arrive at different pressure values. So, this is for u1 value, another point we will have u2 value, another for u3 value, another for u5 value, all these things that can be, we can locate this point thermodynamically for where we can arrive at the final pressures. So, what we try to, and for all these cases your slope remains same, it has, that is slope is corresponding to u1 by v1 square. So, and of course, these points are discrete point, because this is not an isentropic flow, because this is a discrete point, since the shock process across a normal shock is non-isentropic. So, this is, so that way if you put this discrete point, we can make a dotted line and this dotted line represents an irreversible process. And such a curve we call this as a Higonate curve. And this Higonate curve, each point on this Higonate curve represents different shock with different upstream velocity. Point 1 on the curve is the coordinate of upstream pressure and specific volume. Slope of the curve can be calculated from the known upstream velocity and specific volume. Consequently, point 2 it represents the conditions of a normal shock for a specific input case, that is P1, V1 and E1. So, other inferences that we can draw here, that Higonate curve is the locus of all possible pressure specific volume conditions behind a normal shock of various strength for a specific upstream value. Each point in the Higonate curve represents different shock with different upstream velocity. Initial point corresponds to an infinite weak shock. That means, initial point, first change is the weak shock, that is a Mach wave. So, we will talk more details of Mach wave at later point. Locus for all possible points occurs in the upper branch of the Higonate curve, because once we fix the initial conditions, all other points we call this as a upper branch. We cannot extend this towards the lower branch. The straight line joining from initial state to final state, that is called as a Rayleigh line. It always drawn upward, that leads to decrease in the specific volume. Downward slope of Rayleigh line will create an impossible solutions, because for that because it will violate second law. So, in this way, the basic summary for the Higonate curve is that all thermodynamic states across a shock can be located graphically on an Higonate curve. So, in the first part of our lecture, we covered entropy change across a normal shock, Crocos theorem and Higonate equations. Now, I will talk about one of the important aspects of this compression theory through shock wave, that is called as shock wave as a compression mechanisms. So, this particular method of compression is very helpful, or is helpful for the design of wave engines, because normal shock is essentially a shock wave, and we have examined that across a normal shock there is a sudden increase in the pressure and sudden increase in the temperatures, which means flow the streamlines experience rise in the pressure as well as temperature. This is something related to, that means flow field is compressed. Now, if it is a compressed thing, then we can say that wave has the ability to compress the flow. So, if this is taken as a tool, then we can think that a normal shock is can be associated with a compression mechanism process. So, this is what the basic information that we carry, and when you talk about ramjet and scramjet engines, they are normally considered as a wave engines, in which there is a duct in which a normal shock travels, and through these normal shocks we can generate a high pressure and temperature of air, through which we can ignite the gas or charge with a fuel, and this gives very high thrust. So, automatically what I am trying to say, that wave engines which is ramjet or scramjet engines use this shock wave as a tool to create a compression process. So, this is what I am trying to say, that what is the advantage of this shock wave compression mechanisms. Now, let me revisit what is the compression process, what we have learnt so far from the thermodynamics, and what is this compression process that we come across now with respect to normal shock. So, a compression process normally involves the increase in the pressure during change of states, and also it involves increase in the density and decrease in the specific volume. So, thermodynamically we view this compression process in a piston cylinder mechanisms. So, when the piston moves towards this gas, it is flow field is compressed. When the piston moves away from this gas, this flow field expanded. This is how we view any kind of gas which is being compressed or expanded in a piston cylinder mechanism. Now, if you assign this piston process through a thermodynamic meaning, we represent them in a polytropic equations, that is P v to the power n is equal to constant. So, putting this n as difference value 0, infinity, 1, 2 and 3, we can devise various number of curves, so which we can classify them as constant pressure process, constant volume process, constant temperature process, constant entropy process or isentropic, adiabatic process. So, that way we can define. So, this is how the thermodynamic view for a compression process. But here, apart from that, nature has another mechanism that compression process can be achieved through a shock wave. So, across a shock wave there is a increase in the density, and through this increase in density, pressure as well as increase in the entropy. So, and also we see flow field is highly subsonic. So, this can be also treated as one of the tool, that shock wave can be treated as a compression process. In fact, through this Hugoniot curve, we also represent a shock process which is a irreversible process. For a given upstream velocity, we can have many number of downstream conditions that is going to have across a shock waves. That means, for m1 value changing from 1, 2, 3, 4 like this, m2 value is also is going to change, but for that we can denote this point on this Hugoniot curve. But this representation is very discrete point because the processes are irreversible. That means, you cannot come back from 2 to 1. So, this Hugoniot curves talks about shock wave compression process. Now, let us try to impose the PV diagram. Now, and this irreversible and it is non-isentropic. Now, let us superimpose these two curves. One is the PV curve for an isentropic process for which n is equal to gamma, and for a non-isentropic process. Now, if you superimpose them, before going for that superimposed curve, then we can say that that thermodynamic compression for an isentropic process is a quasi-static process, while shock compression is governed through the Hugoniot equations. And these are the relations I have already mentioned in our previous lecture. Now, by superimposing these two curves, we can get a basis, and of course, through a normal shock we get the increase in the entropy, and we also get increase in the static pressure, and since there is increase in the static pressure, this can be visualized as a device for compressions. So, now we are going to superimpose the Hugoniot curve, which is a shock wave based compression, with an isentropic curve which is governed by P v to the power gamma is equal to constant. So, what we see that for a given initial conditions for both the curves, let us say that if you take about P v to the power gamma is equal to constant for an isentropic curve. So, this is isentropic, this is non-isentropic, and this is what we call a Higoniot curve, and Higoniot curve is irreversible. That is why it is represented as a dotted line, and isentropic curve is a reversible process. Now, let us say that if we fix for a given initial condition point 1 is fixed. So, we can write for an isentropic curve P 1 V 1 to the power gamma is equal to P 2 V to the power gamma. So, knowing these initial conditions, and if you go along this for a given value of compressions, given value of V 2, we can have different values of P 2. So, that is what this compression process proceeds towards left hand side. So, on this curve we have different values of pressure and temperature, pressure and specific volume in the downstream. Similarly, on this Higoniot curve we can draw a slope, that is u 1 by v 1 square negative slope, and the wherever it crosses we say it is a 0.2. Now, let us say from point 2 you draw a vertical. So, that value is V 2. So, what it means that for a given value of compression from V 1 to V 2 or compression ratio, that is V 1 by V 2, we find that corresponding pressure value that for an isentropic compression case is P 2 dash, and corresponding pressure value for an Higoniot compression or shock wave compression is P 2. So, obviously, looking at this particular figure, we can say P 2 is greater than P 2 dash. So, what the summary you can make out that for a given value of upstream conditions, Higoniot curves gives higher compressions as compared to corresponding isentropic compression. So, in other words, we say shock compression is a better approach or is much more efficient as compared to isentropic compressions. Another important parameter we can see that in the beginning part of these compressions, we can say that Higoniot curve and isentropic curves, they have deviation is very less. That means, in the initial stage of compression process, both the values are same, but when you go for higher probe field or higher Mach number, there is a large deviation. That means, shock compression is much more effective as compared to isentropic compression, which means shock compression gives higher value of pressure. So, this is the basic tool that we call as mechanism of shock wave as a compression device, and that has led to the evolution of future generation high speed flights integrated with ramjet and scramjet engines. And most important part of this is that when you talk about thermodynamic basis compression, we normally explore piston cylinder type of device or any rotating elements, turbines, compressors. But here in this particular shock compression process does not require any kind of mechanical device or rotating components. So, it means that shock wave compression is considered as a wave based compression which does not require any mechanical parts or components. So, this is the basic underlying fact that the evaluation of ramjet and scramjet engines for aerospace and space science community. So, this is all about the contents of this lecture. Now, before closing this, let me try to solve one specific problem pertaining to what. So, this particular problem is on change in entropy across a shock. So, the problem statement goes like this: the static pressure is measured at 0.4 bar at a point in a supersonic flow. When a pitot probe is inserted at that point, the pressure measured is 3 bar. So, how is it possible? So, obviously, there is a pressure jump that shoots up from 0.4 bar to 3 bar. That means, obviously, there has to be a normal shock. So, if you can draw this schematic about this flow field, so what we see here is a flow field involving pressure of 0.4 bar, and this is maybe a test section. On this test section, we have introduced, so we are measuring at this cross section of this test section as this velocity. Now, we have introduced a pitot probe at this point. So, pitot probe shape goes like this. So, obviously, it encounters a bow shock. But more specific is that flow along this in the vicinity of this pitot probe behaves as a normal shock. So, you can draw this phenomena as here as a normal shock. And flow field before that is P1, that is 0.4 bar. So, streamline encounters a normal shock, and after this normal shock, this probe measures the pressure of 3 bar. So, since it is a shock wave, and when the pitot probe and the flow comes and sees this particular point on the probe, as if it becomes stagnant for a particular instant. So, obviously, that means this acts as an obstruction in the flow field, as if for a certain flow time the flow becomes stagnant. So, for that case, this pressure which is measured here is to be regarded as P naught 2, that is stagnation pressure after this normal shock, and that is the catch here, that we must say that this pressure is 3 bar, that is stagnation pressure. So, basically we are known with this number. So, we can now find out, so we know these two pressures, then we can find out the relation what is P naught 2 by P naught 1, P naught, because this ratio is P naught 2 by P 1. So, this is nothing but your Rayleigh-Pitot equations, and that ratio is 7.5, that is 3 bar by 0.4 bar, 7 bar, and this is a case for normal shock. So, what we have to do is we have to refer a normal shock table that involves this ratio P naught 2 by P 1. So, here it is the normal shock table. So, in this normal shock table you have to refer P naught 2 by P 1 relations. So, this is the catch here. So, you have to see this relation, that is P naught 2 by P 1. Now, closure value of 7.5. So, 7.5 comes somewhere here. This is about 7.592. So, approximately we can say this corresponds to M1 of 2.35. Now, you can easily say M2 is 0.5286. So, this is subsonic, this M1 is 2.35, means it is supersonic, and it is subsonic. Okay. So, we are able to get, but our main attention is that we have drawn this shock pattern at this point, which is a bow shock, and here we have close to the in the vicinity of central streamline, the bow shock behaves as a normal shock. Then we need to calculate the entropy change across a normal shock. So, you have to recall this entropy equation. There are two methods in which we have dealt with entropy change. One is through stagnation pressure. So, through stagnation pressure we write this equation, that is changes of entropy, that is S2 minus S1 is equal to minus R ln P naught 2 by P naught 1. Now, we have this Mach number of 2.35. For this line we need to find out what is P naught 2 by P naught 1. So, P naught 2 by P naught 1 term is here. So, this number is 0.5615. So, this means (5615). So, means S2 minus S1 will be minus R. R stands as 0.287 ln 0.5615. So, which means S2 minus S1 is equal to 0.1656 kilojoule per kg Kelvin, which means your S2 is greater than S1. Okay. So, this is first method through which we can calculate the entropy change through information of stagnation pressure. Now, we have again another method, that is through static pressure and temperature. So, you have to recall the entropy equations, that is S2 minus S1 is equal to minus R ln T2, this entropy equation is Cp ln T2 by T1 minus R ln P2 by P1. Now, here catch is here you have to use ratio of T2 by T1 and P2 by P1. So, that number we have is here. This is P2 by P1 and this is T2 by T1. So, for M1 is equal to 2.35 and this will implies P2 by P1 is equal to 6.276, T2 by T1 is equal to 1.993. Now, when you insert this value and you have Cp is equal to 1.005 kilojoule per kg Kelvin. So, this will give you S2 minus S1 is equal to 1.005 ln 1.993 minus R ln 6.276. So, answer is from this method 0.166. So, here also this is 1.56 and both the numbers matches. So, there are two methods or two routes in which we can find out the entropy change across a normal shock, one through stagnation pressure current relation, through other with entropy equations. So, with this I conclude. Thank you for your attention.